All right, so let's get started. So you see here two charges, a dipole, right? And one charge is positive, the other one's negative. They have the same magnitude. And the picture that you're used by now to looking at is a picture where at different points in space we assign a vector. We've coded here with color to indicate the strength of the electric field at different points. So that will be the way to represent the electric field vectors. As I said before, the alternative to not having color is to draw the lines with a length proportional to the strength of the electric field, but that kind of gets a little bit crazy because when you're too close to the charges, the electric field vectors are really long. So that would not look pretty. So this is one way, but then the other way that you can do, which is called the electric field line, to draw the field lines, is you say you start at some point, you're standing here, and you move in the direction that the electric field is pointing. So you move, if you're here, then you move in that direction a little bit. You stop, and you evaluate in what direction is the electric field pointing now. So you move here, and now you're here. You're like, oh, it changed direction a little bit. So I'm going to move now in that direction. So you move in that direction a little bit. You stop. You measure the electric field at that point. You see in what direction. Every time I look at it, I lose track of where I am. You stop there, look in what direction the electric field is pointing, move in that direction, stop, and so on and so forth. The line or the trajectory that you end up describing, you can sort of trace it here by following a set of lines of arrows. The trajectory that if you start here that you would end up doing will be some curve like this, right? So you can draw that line, and what that line looks like is this. One of the lines one of the trajectories that I was following, maybe it was this one, right? But if you start at a different point, then you move along the direction of the electric field in one direction, and then you evaluate and do what I just told you, and you end up doing a path that looks like this and starts at the positive charge and ends at the negative charge. So all of these lines tell you information about the electric field in the space around a distribution of charges, whatever the distribution of charges might be. So these electric field lines have four main properties. The first property is that they're tangent to the electric field at a particular location. So if you look at a point, say over here, the electric field line has that shape, right? If you draw a line that is tangent to it, that should coincide with the direction of the electric field at that location. So maybe if we toggle back to the field vectors, you'll see that because the electric field line here was flat, it curved this way, the tangent to that line, which is a line like this, horizontal, should be coincide with the direction of the electric field at that location. So for example, along this line, you would expect that all of the electric field lines should be horizontal. They should have zero slope at that point. And that's what you see there, right? If you're moving along this line, then here is the slope is zero slope, and so on, all along this line, right? So that's one of the important properties, that they're tangent to the electric vectors, electric field vectors. The other important property is that those lines are, the density of the lines is proportional to the field intensity. The density of the lines is proportional to the field intensity. So the points in space where the electric field is more intense, you will have more electric field lines at those locations. They will be more packed together, right? So, for example, here, you see that those lines are, the density of the lines is very high, right? Same as here. Not so much, say, over here. So that tells you that the electric field intensity over here is higher. The electric field here has a higher value in magnitude than the electric field, say, over here. Okay? So the density tells you the intensity of the electric field, which is in the previous, when in the plot where we're doing the little arrows with color, remember that the intensity was given by the color of the arrow. Here is the density of lines what tells you the intensity. Another property which is derived from the fact that the electric field lines are tangent to the electric field vectors is that those lines do not cross. You will never find an electric field line plot that has two lines intersecting. That cannot happen. One is that if two electric field lines were to intersect at that location, then you would have the value of the electric field, or the direction of the electric field will be ambiguous. It will not be determined uniquely. Electric field lines crossing like this. This line tells you that the electric field at this location points that way. But this line, the other line that is crossing, tells you that the electric field points in that direction. You cannot have two different directions for the electric field at one point in space. So that doesn't make sense. They do not cross. And the final property that they have is that the star at positive charges, as you can see here, we put little arrows on the electric field lines to indicate in which direction they are pointing, right? In which direction the field line is, say, flowing. So that direction, it's always going from positive to negative charges. There is an exception to this rule, or I should say this only works if you have static charges in space. When we talk about magnetism and a magnetic field changing in time, we will see that a magnetic field changing in time produces electric field lines in space, and they actually loop around. They don't start at a positive charge and end at a negative, they just form loops like this. So, but if you're talking about static charges, no magnetic fields around that are moving, that are changing in time, then it is true that every electric field line starts at a positive charge and ends on a negative charge. Let's look at a different distribution. Let's go back here. Let's look at configuration B. And so in configuration B, we have 4 charges, 1, 4, 2, and 3 here. I'm going to move them around just to set them up a little bit more symmetrical. That's not really important, but, and I also wanted you to see how the vectors move around when I move the charges around, which is kind of nice. All right, I'm just going to put it there. So let's try to think about these properties and see if we understand some of this. So for example, let's start with which charges are positive. Can you tell when you look at the electric field lines, which is what I wanted to show you, can you tell which charges are positive and which ones are negative? So the electric field lines, as we said, underneath here you can read that they start at the positive charges and end on negative charges. What about 4? Are the electric field lines ending at 4 or starting from 4? You see the little arrows are all pointing to 4. So that means that 4 is going to have to be a negative charge. Right? The electric field lines end on negative charges. 1. What about 1? The electric field lines, you see that they're originating from 1. Moving out this way, that way, and so on. That means that 1 is positive. Right? What about 2? Electric field lines coming out of 2 make this one positive, and 3 negative, because the electric field lines are going towards 3. So negative charges are like sinks for electric field lines. They all come into the sink, and positive charges are like sources of the electric field lines. Where do you guys think that the electric field is going to be most likely 0? So which of these 4 properties should help us answer that question? The tangent won't help very much, because if an electric field is 0, it doesn't have a tangent, right? So it gives us no information about the tangent. What about the second one? The density of the electric field line should be proportional to the field intensity. So if you have an electric field that vanishes at some point in space, what would you expect for the density of the electric field lines in the neighborhood of that point? Low density, low electric field strength, so 0 electric field should have 0 density, right? So there should be a place in space where there are no electric field lines. It's devoid of electric field lines, right? So you would expect that the point where the electric field is 0 should be somewhere here. I can't tell exactly where, right? We will need more precision, draw more electric field lines to pin that down more precisely, but should be somewhere in this neighborhood, because you see a hole there, right? You could have said, well, what about here? Right? I said the electric field, the point in space where the electric field is exactly 0. Not just small in magnitude, but exactly 0. right? That wouldn't happen here because you know that these are point charges. So if you move away from them, they're going to act as if they were a distribution of charge with, say, a net charge of whatever it is here. This one is negative, positive. You add all those charges, and you will end up with electric field lines pointing away or towards the whole distribution of charges. So out here, you would expect the electric field that, yes, if you move far away, the electric field will be small and small and small as you move far and far away, right? But there's no reason to expect that it will be exactly zero, right? But here, we have electric field lines that have the density around this point is not zero, and there is a point where there's no field lines. Let's see if we can figure that out from the electric field vectors. At that point, somewhere along this, around this point, you will have the electric field. The electric field is the superposition of the electric field of all of the charges, right? Now you can see that 1 and 4, one is positive, the other one's negative. They kind of look the same magnitude. So it looks like 1 and 4 are a dipole, and 3 and 2 are also a dipole. 3 seems to be negative, 2 seems to be positive. So somewhere here, the electric field produced by 1 and 4 is pointing up. That's what the electric field along this line looks like for a dipole. And the same should be true for 2 and 3, so it should be pointing down this way. So the electric field produced by 2 and 3 points down, the electric field produced by 1 and 4 points up. Since you're closer to 2 and 3, it's very likely that that electric field down is going to compensate the electric field up of 1 and 4 and produce a 0. Okay, so that should tell you that that does make sense. Should be a 0 somewhere here. Which of these charges have the highest value, the biggest charge? So move around a circle around each one of the charges and see what is the density of field lines around those charges. So if you move in a circle around 4, notice the density of the lines. They're pretty packed together. The same seems to be happening with 1 if you move field lines in that little circle. Now if you move around 2, you cross a smaller number of field lines. If you move around 3, you actually could count them, and maybe this is like 12 and this one is like 14 or 16. If you move around 3, you find about 16 field lines moving in a circle. Okay, so that tells you that 1 and 4 are the biggest charges, right? Because the field strength near them is bigger than the field strength near 2 or 3. So you would say 1 and 4 are the particles that have the highest charge in absolute value. Then the next one is 3, and the smallest charge seems to be 2.